Welcome to this explainer. Look, if you're aiming for top marks in your Class 10 science exam, you already know that Chapter 1 is the foundational bedrock of all things chemistry. So, we're taking your dense revision notes and transforming them into a high-octane cheat sheet designed specifically for the CBSE 2027 pattern. We're going to break down these concepts step by step to guarantee you don't just memorize, but actually understand the core material. So here's what we're looking at today. First, the basics of reactions. Second, balancing those chemical equations. Third, the core types of reactions. Fourth, corrosion and rancidity. And finally, some pro tips for board exam success.
All right, let's jump straight into Section 1, the basics of reactions, spotting a chemical change.
Simply put, a chemical reaction is a total transformation. It's a process where your starting materials, the reactants, completely change into entirely new substances, which we call products. And these products, they have completely different properties from what you started with. A classic example is when you take solid magnesium, mix it with oxygen gas, and get a white powder called magnesium oxide. It's literally a complete chemical makeover. But you might be wondering, how do you actually know this invisible transformation is happening? Well, if you're watching an experiment and you spot any of these clues, boom, a chemical reaction has officially gone down. Maybe a perfectly clear liquid suddenly turns bright yellow, or the test tube actually gets physically hot in your hand. You might see gas bubbles fizzing up, or a solid, a precipitate, just forming out of nowhere. Even a sudden change in state, or honestly, a distinct new smell, are massive giveaways. Now check out how we write this stuff down. We use a chemical equation with precise symbols instead of writing out long, clunky sentences. Look at the left side. Hydrogen plus oxygen gives water. I mean, it's descriptive, sure, but look at the right side. 2H2 plus O2 gives 2H2O. This right here is the true language of chemistry. It's concise, it's universally understood, and most importantly, it tells us exactly how many atoms are involved in the dance. Moving right along to Section 2. Balancing chemical equations, cracking the chemical code. Okay, before we balance anything, we have to understand why we balance. It all comes down to the law of conservation of mass. This is literally the golden rule of chemistry. It dictates that you absolutely cannot magically create or destroy matter in a reaction. What goes in must come out. So the total number of atoms for each element on the reactant side has to perfectly match the total atoms of that same element on the product side. No exceptions. So how do we actually do it? Just follow this exact sequence to reliably balance any equation. First, write down the unbalanced equation. Next, systematically count the atoms on both sides. Now listen up, because here is the insider secret that'll save you from tearing your hair out. Balance one element at a time and always leave hydrogen and oxygen for last. Seriously, they tend to be everywhere, so they often just conveniently balance themselves out if you handle the other elements first. And finally, always do a quick recount just to be sure. Let's level up to Section 3, Types of Chemical Reactions, the core reaction formats. This slide brilliantly highlights a favorite 2-mark board question: reactions that spit out heat versus those that basically eat it up. On the top, we've got exothermic reactions. Think exo for outside, thermic for heat. Heat is released. Respiration, the very process keeping you and me alive right now, is actually an exothermic reaction. On the bottom, endothermic reactions absorb heat. For instance, if you want to break down calcium carbonate into calcium oxide, you have to constantly supply heat just to keep the reaction going. Okay, right here is your ultimate cheat sheet for the 4 primary structural types of reactions. We've got the general format and a classic example for each. Combination is super simple. 2 things join up to make one. A plus B becomes AB. Decomposition, that's the exact opposite. One compound breaks down into 2 or more pieces. Then there's displacement, where a more reactive element essentially bullies a less reactive one right out of its compound. And finally, double displacement, that's just a complete partner swap between 2 compounds. Take a mental screenshot of these formats, they're super important. Let's do a quick test. Listen up, because this is a competency-based question pulled straight from past board favorites. A white solid turns gray on exposure to sunlight. Can you identify the compound and figure out why it's stored in dark bottles? Just think about it for a second. Did you get it? The answer is silver chloride, or AgCl. The big secret here is photolytic decomposition, meaning it's a reaction triggered specifically by light. The sunlight literally breaks the chemical bonds, turning that white silver chloride into gray silver metal and releasing chlorine gas. And honestly, that is exactly why those silver chloride bottles are kept safely in the dark in your school lab. If they were in clear glass, the light would ruin the chemicals before you even got the cap off. Now, let's talk about a specific outcome of some of those double displacement reactions we mentioned earlier. If a reaction creates an insoluble solid that just sinks to the bottom of your test tube, you've got yourself a precipitation reaction. This is a massive VIP concept for your exams. A classic example you absolutely need to memorize is barium sulfate. It's this bright white precipitate that appears the instant you mix sodium sulfate and barium chloride solutions. Next up, we've got a set of reactions that are basically two sides of the same coin. Lock down this visual split to easily master another classic two-mark difference. Oxidation is simply gaining oxygen or losing hydrogen. Reduction is the exact opposite, losing oxygen or gaining hydrogen. And when you combine them, you get a redox reaction. Red for reduction, ox for oxidation. They always happen together. Check out this example. Copper oxide plus hydrogen gas gives copper plus water. The hydrogen gains an oxygen atom, so it's oxidized. But at the exact same time, the copper oxide loses its oxygen atom, meaning it gets reduced. So one element steals oxygen, while another loses it, all at once. Moving right along to Section 4, corrosion and rancidity, the real-world villains. So we're leaving the test tubes behind for a minute to see how oxidation acts as a real-world villain. First up, corrosion. This is your metal's worst nightmare. It's the slow, steady eating away of metals, and it needs both oxygen and moisture to trigger the destruction. You've seen this literally everywhere. Iron rusting and getting flaky, silver jewelry developing that black tarnish, or old copper coins turning green. That is slow-motion oxidation just destroying structural integrity. On the flip side, we have rancidity. This is what happens when the fats and oils in your favorite snacks oxidize. Have you ever opened an old bag of chips and been hit with that awful, stale, almost sweaty smell? Yeah, gross, right? That's rancidity at work. The oxygen in the air reacts with the fats, making them smell terrible and, trust me, taste even worse. But hey, chemistry also gives us the solutions to fight back. Here's your arsenal for defeating these villains. For metals, you can block out the oxygen and moisture by painting, oiling, or greasing them. You can also use galvanization, which is a super clever way of coating iron in a protective layer of zinc. For food, we fight rancidity by storing things in airtight containers, tossing them in the fridge to slow the reaction, or, my personal favorite, flushing potato chip bags with inert nitrogen gas. That way, there's absolutely no oxygen left inside to spoil your snacks. All right. Final stretch. Section 5, Board Exam Success Tips, the boss fight preparation. Definitely take a screenshot of this rapid-fire checklist because doing these 6 things will practically guarantee you don't lose silly marks. First, memorize those 11 key equations from your notes. Second, do not ignore the NCRT activities. The boards love pulling case studies directly from there. Practice balancing every single day until it's pure muscle memory. Make sure you use the exact CBSE wording for your definitions, focus heavily on competency questions that ask why things happen, and always draw neat labeled diagrams. 100. That is your target score out of 100 if you apply these concepts efficiently. And you know what? It's completely achievable. If you use structured revision and actually understand the visual and logical flow we've gone through today, you'll nail it. Don't just passively read the textbook. Really visualize these reactions happening. To wrap things up, look around your room right now. Seriously, take a look around. What unseen chemical reactions are happening right beside you? Maybe it's the lithium-ion battery in your phone oxidizing to give you power, or a tiny bit of moisture causing slow corrosion on a window hinge. Chemistry isn't just some chapter you have to pass. It's happening all around you every single second. So keep observing, stay curious, and start seeing the world through the lens of reactants and products. Thanks for joining me on this explainer, and good luck with your revision.